Okay, off we go. Thanks for coming. Last day before break. Don't forget about the attendance quiz, attendance code, right? Of course, don't want to forget that. Clock's ticking as usual, a minute and a half or so left. Let's pick up where we left off. We were talking about how to turn double integrals into iterated integrals, right? Double integrals are important because that's what allows you to actually make connections to real world applications, right? It's not mathematician, abstract, entertainment, right? It's actually, this is how you make connections to applications. Rewriting them as iterated integrals is important because that's what we know how to compute. That's where we can apply the fundamental theorem of calculus. Okay. All right. So, one more example. Well, I'll say another example. We're going to consider this domain here bounded by, two curves, two parabolas, a parabola and a line, and that gives us, this region here. We're going to do this one both different ways. We're going to do it dy dx, then we're going to do it dx dy. We're going to see how they worked out differently, and then we're going to try to learn a lesson from how this example plays out. Okay, so here we go. Let's start with this top version, this top approach. And I'm going to go through these relatively quickly because we've done several of these previously. Starting with our x slicing. Well, x goes from there to there. It's -2 to 2. And where did I get these values? Well, it comes from looking at these points where these two curves intersect, and a little bit of geometry, a little bit of algebra makes that pretty straightforward, I think. We're going to then fix a value of x, as we've done before. We're going to focus our attention now for that value of x just on this x slice. Right? And as we move across that x slice, we're going to need to figure out where does y start and where does y end. In other words, we want to find the bounds for y. Well, y, let's see, the lower bound for y comes from that point right there. That point is on this curve. That curve has this equation, and remember, it's so easy to lose track, forget what you're doing. We are looking for a y bound, right? And so in this equation, we solve for y. And it's pretty easy to solve for y. Y's already been solved for. The function of x that tells you y is x squared. Okay, upper bound comes from, there it is the upper bound, comes from that point. That point is on that curve. That curve has that equation. And again, remind yourself, we're solving for y because we're looking for a y bound. Again, easy to solve for. And so, boom. Okay, fine. Now let's do it the other way. See what happens. Same domain. Right? Okay, this time starting with y slicing. There's our range of y slices, right? Y slices look kind of like this, and as we go across the whole domain, you'll notice we start here, where I'm going to say, whoops, I missed, where I'm going to say it's pretty clear y is 0. This is the origin. Right? And then y is going to end. Well, here's our last slice. Our last slice is literally the line y equals 4, and the value of y when y equals 4 is 4. Right? So again, sometimes they're easy, sometimes they're just staring at you. Okay, again, per usual, we're going to fix a value of y now. That is, fix a value of the outside variable. X then ranges as we move across that y slice, and we play the same game. The lower bound, looking at x, the lower bound for x comes from that point. That point is on this curve. That curve has that equation. Here's where students mess up. I see the following mistake a million times. A lot of students will say this curve has that equation. Boom, x squared. Real easy to mistake and think that the bound should be x squared. It's not. We have to solve for x. we are looking for an x bound. I need my x bound to be a function of y. I need to solve for x as a function of y, not y as a function of x. Does everybody see that? Is everybody comfortable with that? Right? So x squared, first of all, x squared wouldn't even make any sense. A bound on x can't be a function of x. It just doesn't make any sense, right? Okay. All right. So we solve for x. And let's see here. Solving for x, you can see you're going to get either plus or minus square root of y. Now, which one should we take, the plus or the minus? And here's where a picture can be really, really helpful. It's one of several ways that a picture can be really helpful. We're looking for this lower bound, and I can just see right here on the picture, the one I'm looking for, this lower bound is clearly negative. And so, negative square root of y. Okay. Similar process to find the upper bound. Again, looking at x bounds. There's the upper bound. It comes from that point. That point is on that curve, which has that equation. Again, careful, don't forget. We need an x bound. We're solving for x. And solving for x, here we get plus square root of y, because again, thank you, picture, clearly we're looking for a positive value of x. Is that cool? Everybody with me? Okay, so that's two more examples. Now, the point to these two examples is to learn a lesson. I claim that this is a very nice example of the lesson I want to communicate. First of all, let's ask ourselves which one of these options we like better. I have a pretty strong preference myself. I like this one better. I think this one looks scary, and it's because of the square roots. Now, you might be thinking to yourself, who cares? The square roots are in the bounds. You just plug them in at the end, whatever. Well, kind of. The thing is, they're in the bounds for the inside integral. Yes, you will plug these in at the end of doing the inside integral, which means those square root of y's are going to be part of your outside integrand. Now you're doing antiderivatives of expressions that have square root of y in there. And that's those are ugly integrals, right? We all else being equal don't want square roots in our integrands. Does everybody see that? Okay, so clear preference. All exceptions granted. I mean, it's possible depending on the f. I suppose it could be that, who knows. Most of the time, we're going to take this one. Now, how can we arrange to do this right in advance without having to work out both of them? Right? So, I mean, as it stands, we've worked out both. I did a bunch of work to work out both of these. I would like to have a simple rule that will direct me to the correct choice. Let's be realistic. Most of the time, right? And here's my take on that. Why did I get the square roots? And roughly speaking, I got the square root because by putting dx on the inside, I arranged for a situation where I was going to need to solve for x. And solving for x is what gives me these undesirable bounds. Whereas the first way we did it, we had dy on the inside, which arranged for I would just need to solve for y, which, again, whichever one of these y's you have to solve for, nice. No square roots. Everybody see that? So I'm going to call the moral of the story here is, notice you don't even really have to even look at the picture. You can just look at the statement of the question, right? And just by looking at the algebra and the statement of the question, ask yourself the question. Forget about the picture, not even looking there, but would I rather solve for x or y? And I don't want to have to solve for x. Simply seeing that I don't want to have to solve for x tells me I'm not going to put dx on the inside. Does that make sense? I think it's a really good rule of thumb. I do this all the time. This is one of my primary guides to how to make good decisions on which way to slice. Here's another example where we're going to do it both ways, and then we're going to learn a lesson. Moving quite a bit faster this time. Y 0 to 1. Pretty clear. Fixing a value of y, looking at the resulting range of values of x. The lower bound comes from that point, which is on that curve, which I can solve, and x is y. The upper bound comes from that point, which is on that curve, in which I can solve for x, and I get that function 2 minus y. No big, right? Straight up process. No problems. Let's do it the other way. dx on the outside, it would seem that x goes from 0 to 2. You'll notice that's not what I wrote down. It would actually be a real problem to write x as going from 0 to 2. Let me show you why I did what I did instead. Instead, I did x from 0 to 1. And then subsequently, x going from 1 to 2. Reason is, let's look at the inside bounds. In particular, I want to look at the upper bound for y. The upper bound for y is going to come from points like that are on this line. Solve for y, you get that function. But for these other values of x, for the greater values of x, when x is between 1 and 2, the upper bound from y is going to come from points like this that are on that curve, which gives this upper bound for y. We get two different formulas. Right? I can't make a single iterated integral that has x going from 0 to 2, because both of these formulas would need to be my upper bound for y, depending on which x we're talking about. And I can't put multiple formulas in the same position as the inside upper bound. They just can't. It doesn't make any sense. So that's the downside of this approach. Now again, which do we like better? I think it's a pretty easy choice. All else being equal, and counterexamples granted, don't come up very often, but all else being equal, I'd rather do one integral instead of two integrals, right? I mean, surely? Okay, so again, how do we anticipate this? So we don't have to write it all out in advance first. What's the simple guide that will help us avoid even having to explore this option? And here's my take. My take is, the problem happened because the points determining our upper bounds jumped from this line to that line. These greatest values of y for any given x went from the red curve to the green curve. Now, how did that happen? How did this sequence of points jump from one curve to the other? Well, because they intersected. What happens when two curves intersect? Exceptions granted, but generically it gives you a corner. So this is my my little rule. When you are thinking about how to slice, and once I've decided, for example, I'm going to do dx on the outside, as I go in the x direction, as I'm making x slices, watch out for situations where you slice through a corner. When you slice through a corner, that inside bound, some version, in this case the upper inside bound, could be the lower, every domain is different, but that's the situation where, probably the inner bounds are going to change formulas, and I'm going to have to start a whole new integral. I'm going to have to stop the integral I was working on. I'm going to have to start a whole new integral to finish up the slicing with the different formula. So the moral is, try not to slice through corners. It's real simple. Just look at your slicing process, and if in the middle of your process you're slicing through a corner, yeah, you're setting yourself up for one of these undesirable outcomes. Okay, now there's an asterisk to this. You will notice that even with this ordering of things, and as I was going this way, the very first thing that happened is I sliced through a corner, right? That's a corner, that's a corner. Of course, we've already talked about that one. So what's the problem with slicing through that corner? Well, there's no problem slicing at the beginning because I was starting a new integral there anyway. And there's no problem slicing through a corner at the end. I was going to end that integral anyway. Right? So when I say don't slice through a corner, what I mean is in the middle of your slicing process. At the start, sure. At the end, fine. But not in the middle of the process. And roughly speaking, that corner, slicing through that corner as I go in the X direction is why I had to stop at 1 and pick up from 1 with a new integral. Let's look at the other direction. See how everything's fine if you do your dy integral on the outside. Again, corners being where they are. Sure, I start by slicing through corners. Yeah, I was going to start a new integral there anyway. All good, all good, all good. I end slicing through a corner. Fine, I was done anyway. No problems. Single iterated integral. Life is good. Everybody good? So we have a couple of good little guides here to help you make good decisions on which way to slice. Think about what variable you want to solve for. Look at the algebra that's given, or you might have to do some algebra to see what the algebra of the curves is. Try to decide what variable you'd rather solve for. Put that on the inside. Right, again, whichever one you want to solve for, put that on the inside. The other rule, try not to slice through corners. Notice these guides don't address every possible circumstance. The corner guide doesn't give any advice on which way you can slice either order. There's no corner issues in either direction on this example. There's no preferred variable I'd rather solve for in either of these. Likewise. Right? So you need both rules to handle different circumstances. In those situations where both of them suggest a choice, they tend to agree. That's the really good news. Okay, moving along. Another example, sometimes the domain's not given. In fact, you'll notice in this case it's not even given that we should use an integral at all. The question just says you've got this paraboloid and you've got this plane, and we are interested in finding the volume. Finding the volume that's in between. Right? No discussion of integral even. Excuse me. So how do we proceed in a case like this? The way I like to think about this is keep in mind what a double integral is. A double integral is where you're chopping stuff up into pieces and then adding up those pieces. Right? So even though we don't have a domain, what I'm going to do is I'm still going to go ahead and take this thing and chop it up into pieces. As I chop this up into pieces, I'm then going to ask myself, what could I call a domain that gets chopped up to the same pieces? Right? Corresponding pieces. So I'm going to suggest that we chop this in both vertical directions. So we're going to slice this. Let me just hand wave. We're going to slice perpendicular to the x-axis. We're going to slice perpendicular to the y-axis. And the result is this whole volume is going to turn into a bunch of little French fries, like so. Right? Now I make the observation that the total volume is the sum of the volumes of these individual slices, these individual French fries, right? And so I can, this would not be unreasonable to try to do this with an integral. Okay, now next question. As I do all this slicing, right, I'm slicing perpendicular to the x-axis, perpendicular to the y-axis, what else gets sliced up into perfectly corresponding pieces? And I propose the shadow of my solid. The projection of that solid straight down into the xy plane. As you slice up the solid, you're going to also effectively be slicing up this shadow. And in fact, for every French fry, there is a corresponding little piece of the shadow. For every piece of the shadow, there's a French fry. For every French fry, there's a shadow. Everybody buy it? So what I can claim then is I can say, look, the sum of the volume is the sum of the little smaller volumes, and furthermore, we can compute each one of these smaller volumes as associated to a little piece of this domain. So that's going to be our domain. How we doing? Everybody happy? I want to remind you all of another thing. If I can get this to cooperate. There we go. This goes back several pages, back to when we were defining double integrals in the first place. Remember, for each little piece, right, there's this tendency to think about double integrals as volume under a graph. I implore you to try to let go of that as a primary point of view. That's an incidental uses here and there. Try to think of an integral as something where for each piece of the domain, for whatever reason, think broadly, think widely, think generally. For whatever reason, you want to multiply something times the area of that little piece. Whatever the quantity is, if there's something times area that gives me the quantity I'm interested in, we're good. That's all you need for this to work. So going back to our situation, is that the case here? And I'm going to zoom for clarity. Is there something I can multiply, colors. Is there something I can multiply by this area to give me this volume? And yeah, totally. This, what you might call height. Right? That height times this area, well, that area is the same as the area of this base. Height times the area of the base is that little piece of volume. Is that cool? Is everybody with me? So forget about this. Again, this idea of the area under a graph doesn't really help us here. But what I can totally say, and I kind of regret my color choices here. Let me do this. Let me make this blue. How about that? The blue area times this green height, which of course you see is just the difference of those two z coordinates. Blue times green gives me the orange volume that I need. Everybody with me? Questions? Feel free. All right, now related question. I've got my domain in some sense. I mean, I've got a picture of it. I have a loose geometric description of it. My domain is this shadow down here, but I don't really have the algebra that I need to actually get my hands on that domain. So, for example, how would I go about finding the equation of this boundary curve for my shadow, whatever this shadow is? And here's my argument. Let's see here. I'll leave that there for the moment. Pick some point in the domain. Let's say this one here, whatever. Some point in the domain. We can talk about how far it is up to the paraboloid. And we can talk about how far it is up to the plane. And those are going to be different. And the difference is the height. Okay. But notice that for a point on the boundary in question, right, looking at the boundary itself, the distance up to the paraboloid and the distance up to the plane are exactly the same. That's the foot in the door. That's how we're going to do this. I'm just going to make the observation. Oh, what did I don't even know what just happened there. What? Oh, it closed that thing. Oh my gosh. Sorry. Yeah, go away. Okay, and now I'm waiting. Okay, sorry. We'll get there. Oop, too far. There we go. Okay, let me rewind that a little bit. For points in the interior of the domain, blue is greater than green. For points on that boundary, the boundary curve that we're interested in, the blue and the green heights are the same. Said differently, Z1, which comes from the paraboloid, is going to equal to Z2, which comes from the plane. So that's where this purple curve comes from. The purple curves comes from setting that Z equal to this Z. Everybody see the geometry on that argument? Here's a different take, if you like. Geometric appeal. The boundary of the shadow comes from it comes from being the shadow of this edge. And this edge is where the two surfaces intersect. The two surfaces intersect where you get the same Z values for a given X and Y. Okay. All right. And so it's all over but the details. You set those two Z's equal to each other. By the way, you can solve for that green Z very easily. The green Z is already solved for. It's X squared plus Y squared. The blue Z is not solved for. Right? This blue Z, I'm going to have to actually do a little algebra to figure that out. Ends up being this. And so setting them equal gives me that equation. And then a little bit of algebra. You got to complete the square in here, right? Completing the square, very handy, continues to be useful. Make sure you're good with that. And the punchline is equation of a circle. So now we know everything we need to know about this domain. This domain is just a circle. There's the exact equation. Everybody happy? Okay. All right. That's section 5.2. On to 5.3. By the way, we're going to finish 5.3 in about 5 minutes. This is a really, really short section. I think it should be an example in section 5.2. It's not a lot goes on in this section. Sometimes you need to change the order of the integral. In practice, this is just a matter of kind of undoing the reversing the process of turning a double integral into an iterated integral and then going backwards. So let's see this in practice. It's a matter of doing it. Suppose you want to compute this thing, seemingly very conveniently already as an iterated integral. We just need to apply the fundamental theorem of calculus twice. Should be straightforward. The problem is the very first thing we need to do is compute the antiderivative of e to the x squared dx, and that antiderivative, we can't do it. Right? I don't know if y'all remember this from Calc 2, but there is no closed form antiderivative. You can't write that antiderivative in terms of regular functions. So we're stuck. All right, so what we're going to do, we're looking at an iterated integral. Here's where we are. We don't like that iterated integral. We can't compute it. The strategy is going to be to reverse engineer the original double integral. Rewrite it as a different iterated integral slicing in the other direction. And sometimes when you do this, it ends up being straightforward to compute. So that's the process. Excuse me. Okay, so here we go. How do we sort of undo this? We are going to, it's pretty much just literally reversing the process that we would normally do to turn a double integral into an iterated integral. I'm going to look at these equations. For example, y equals 0. There you go. There's y equals 0. Y equals 1. Cool. It says right here that y goes from 0 to 1. That means my domain is between y equals 0 and y equals 1. For any given value of y, whatever value of y you might be looking at, says right here that x starts where x equals y, which is that curve. And it says right here that x ends when x is 1. That's that curve. And so, you just write that down and document on your picture, and here's your domain. So the original double integral that gave rise to this iterated integral in the first place is an integral over that triangle. Did you see how that process went? It's literally just kind of interpreting directly from what's in the iterated integral. Okay, so we've kind of taken that backward step. Now we just have to do it forward. And let's be quick about this. We're going to do it in the other order, of course. X slicing first. X pretty clearly goes from 0 to 1. And then for a given value of x, whatever value of x we're looking at, there's my x slice. We start with y equals 0, and we end, well, I guess I don't have anyway, we end with y equals x. And there's our new iterated integral. What do you think? Okay. Now, in this particular case, did this help us? Is this something I can work with? I do still see that e to the x squared there. I'm not super happy about that. A little concerned that might still be a problem. But conveniently, we can at least kick the can down the road a little bit, because my inside integral is a dy integral, which means that x is a constant, which means that e to the x squared is constant, and that makes that a super easy dy integral. The dy integral is nothing to it. It does still remain, of course, that I've still got to do the dx integral, right? How am I going to compute the dx integral? I've still got an e to the x squared in there, but because I already did the dy integral, because I did the switcheroo on the order, now I have this extra factor. Now a u substitution kills it. No problem. Super easy. How are we doing? Everybody see how that, I mean, it's hard to see that coming, right? That would work, but sure enough, works nicely. Okay. All right. So like I say, I think this makes sense as an example in the previous section. I don't know that this deserves to be an entire section of the book, but whatever. It's not my book. So anyway, now we're done with section 5.3. And now we move along. 5.4. 5.4 is a significant section. A lot of stuff to talk about. Triple integrals. Honestly, it's a lot like double integrals. It's kind of the same thing. Not exactly, but pretty similar. Let me go back to, let's see here. Back to here. recall that where single variable integrals come from is that sometimes we have a one-dimensional domain. On said one-dimensional domains, if I chop it up into pieces and if I look at one little piece at a time on each of those little pieces, depending on what the application is, I might be able to write the answer for each little piece as something times length. Right now, sometimes we're interested in area, in which case it would be height times length. Sometimes we're interested in mass, in which case it would be mass per unit length times length. Right? Whatever the application might be, it's going to always, though, be something times length. Okay, now reminder, we generalized this, or extended it anyway, to a two-dimensional domain, but it's ultimately was kind of the same argument of, well, look, we're going to chop it up into little pieces, and depending on the application, the idea is that we try to figure out how to write on each little piece, one little piece at a time, something times area. Now area, because they're two-dimensional, they don't have a length, they have area. And so if you're looking for volume under a graph, then it would be height times area. If you're looking for mass, it would be mass per unit area times area. That gives you mass. If you're interested in population of the state of Colorado, then it's people per unit area times area. Whatever. Right? So same strategy, chop it up into little pieces. On each little piece, write it as something times size. I would say, just for convenience, density times size. And then add up over all the pieces. And the particulars are different, yeah, but it's the same strategy. Chop it up, add it up. Well, sometimes what we're interested in isn't distributed over a length. Sometimes what we're interested in isn't even distributed over an area. Sometimes what we're interested in is distributed over a volume. So here's a real world relatable example. I mean, to me this looks like a fish tank. Let's call it a fish tank. And there's something floating in the fish tank, some sort of pollution or whatever. And maybe for whatever reason the pollution is heavily concentrated around some corner, and then it gets less and less the farther you get away from that corner. But it depends on all three different variables, right? So your pollution per unit volume varies throughout the tank with no, in a way that depends on all three variables. All right, so I want to compute the total amount of pollution. Well, I would chop up my three-dimensional volume now into, well, that's not a sub-interval. It's not a sub-rectangle. I'm just going to call it a sub-box. Right, little three-dimensional piece of volume. And the idea is, again, same ultimate strategy, just kind of different in context. In each little such box, the goal is to try to find how to answer the question for that little box as something times volume. Same pattern. Right, now in this case, if we're looking for pollution, I want to know how much pollution is in this little box. Well, it's going to be pollution per unit volume times volume. That gives me pollution. And then adding up over the entire box gives me the total amount of pollution. Everybody see that's the same kind of strategy, right? Now, details to follow. How do we compute these things? Oh my gosh. Yeah, right? That we'll have to worry about that. But just from a strategy construction standpoint, all this is again, like I like to say, chop it up, add it up. We're chopping up a whole into little pieces such that the question is easy on each little piece, and then we're adding up over all the pieces. Okay. Everybody okay with that? All right. Okay, so for example, let's talk about how to compute mass. How would I compute the mass of a some sort of a solid? Well, the whole is the sum of the parts. Right? That's the nice thing about one of the nice features about mass. It's an accumulating quantity, and on any given little piece, mass is mass per unit volume, which I'm given, times volume. And so, in fact, don't know how to compute this yet, but whatever, once I know how to compute triple integrals, this triple integral will tell me the total amount of mass. Okay. All right, so we're going to get to computation in just a couple seconds, but I do want to talk about whoa, I hit, my finger hit the, okay, sorry, accidentally hit the little button there. Oh, went too far. So I want to talk about intuition a little bit. Here is some intuition we've talked about before. I'm going to call competing intuitions for how to think about single integrals and double integrals. So we've talked previously about how you can view a single variable integral as being area under a graph curve. Right? Everybody's first take on single variable integrals, area under a graph curve, right? Familiar? Everybody remembers this? And now I have my competing preferred take, which is I like to think of single variable integrals as adding up over an interval. Right? I like mass as an example of where I'm adding up over an interval because mass is relatable, familiar, physical, right? But it's a nice stand-in for whatever it is that might be distributed over your one-dimensional interval. Okay. Pros and cons. All right. Now we talked about double integrals, and again, there is this kind of look at the graph. How much space is there under the graph? You can view a double integral as volume under the graph surface. Totally analogous to this. Everyone's first take on single variable integrals. A lot of students therefore like this point of view on double integrals because it's analogous to something that's super familiar. Pros and cons. Again, I like this take. I think this is more broadly useful. Is think of a double integral where you're accumulating stuff adding up over a two-dimensional region. Right? Again, I claim real world out there, how often is it that you need to find the volume under a graph, not as a means to an end, but as an end, as what you're actually interested in? How often is it exactly what you need? I need to know the volume under a graph. Surprisingly rare. Doesn't come up super often. It's certainly not all of what we need to compute. But double integrals can always be thought of, I think, very naturally as there's some sort of an accumulating quantity and it's adding up over an area. And I know there's more to look at there. It's, again, more satisfying in some sense. But, pros and cons. Okay, so this is where we were in terms of integrals and intuitions as of 10 minutes ago. Now let's think about triple integrals. How would we extend this idea of looking under the graph? Well, we're about to have a really big problem. For a single integral, we get a two-dimensional picture. Double integral, three-dimensional picture. Triple integral, the pattern would continue. You should expect this to be a four-dimensional picture, which you cannot visualize. We are mere three-dimensional critters. You just can't do it. Our brains don't work that way, right? So, problem. Right? On the other hand, if you think about integrals the way I've been encouraging, and this is yet another reason why I think this is a valuable point of view. If you think about it as stuff accumulating over an interval or accumulating over a region, how do you think about a triple integral? Yeah, no problem. It's stuff accumulating over a solid three-dimensional region. Fine. Picture. Cool. No conflict. No problem. You can totally extend this analogy, where this one crashes and burns. Everybody see what I'm talking about there? Okay, so this is my second take on why you should think about integrals this way. For one thing, in fact, that's what you're going to be computing. It's very rare that you actually need these things. Incidental situations here and there, right? What you're going to need most of the time is to compute some sort of accumulating quantity. It's a question of what dimension of domain does it add up over? And then you pick the appropriate integral for that. But mostly you're going to be computing stuff that accumulates over regions. Secondly, this one actually makes sense for triple integrals, and this one in red makes no sense at all to three-dimensional human beings for triple integrals. Okay. All right. So now, a last little observation on this. I am going to point out that there are those who will take this point of view on single integrals because, extensive life experience thinking of it that way. And then they'll take this point of view on double integrals because, familiar, natural extension. And then for lack of options, have to try to make sense out of triple integrals this way. And so for one thing, you have a pattern problem, right? Where you've got a totally different take on these different kinds of integrals. One example of where that pattern problem rears its ugly head is volume. We're looking at kind of similar looking pictures for two different kinds of integrals. And I get asked on a regular basis, hey, when I've got a three-dimensional question, how come sometimes we write it down as a double integral and sometimes we write it down as a triple integral? Do I get to just pick, or what's the deal there? Right? And the deal there is that student is conflating these two different kinds of pictures. Right? That's the problem. Right? So if you take this, blue sort of trio of perspectives, you're going to run into that problem on a regular basis, and I find that to be very confusing. So I want to encourage everybody again, try to make sense out of this green sort of consistent green pattern of intuitions for integrals. Okay, enough of that. All right. So how to compute these things? Oh, got ahead of myself. How to compute these things. I made a case for y'all a while ago that double integrals can be computed with iterated integrals. And I gave you an intuitively satisfying argument that you just compute this volume two different ways and boom. The analogous argument, if I were going to try to persuade you that triple integrals can be computed with iterated integrals, I would have to argue that this thing that we can't visualize can be computed two different ways. And I can't make that argument because we can't visualize it. There's no intuition to be had down that road. So I'm not going to be able to give you that intuition. We just don't have the dimensions for it. Good news, it is still true that triple integrals can indeed be computed with iterated integrals. Triple iterated integral, you might say. Now, how do we know this is true? If we can't draw the pictures, if I can't make the geometric argument, well, there are other arguments. In fact, there are much better arguments, much more mathematically solid arguments, but they are surprisingly subtle and delicate and sophisticated, and I don't think they're appropriate for this context myself. There are streamlined versions of those arguments that sweep important issues under the rug, and I think they're misleading. So I'm just going to assert that just like with double integrals, this works fine. We have our strategic picture. Whatever your application is, write it as a triple integral. We need triple integrals because they connect to applications. Rewrite that as an iterated integral. We need iterated integrals because there's something that we can actually compute to get answers. That's going to be our big strategy. And we'll draw the line right here. Call it a week. Y'all have a good break. See you on Wednesday. See you later.
Thank you.
Yeah, sure. See you later.